this has been a hard lecture to attend, right? It's Sunday, and which means that we'll be meeting today, tomorrow, and next Wednesday. It's a very tight chance. You'll be very tired. You'll be very tired. I'm very tired. So, but nonetheless, this is about one of the last 5 or 6 lectures that we have ahead of us. Yes, just count the time, right? Because May the 1st, Li Laomengji is going to be one of our Wednesday lectures. It could have been only one of our Wednesday lectures. So the final week starts on which one? Which day? I can't exactly remember. May the 10th, something like that. So yes. So including this lecture, I think we're having about 6 lectures. And so my plan is, again, as I said, my plan is the following. I would like to, after we finish chapter 6, I would like to talk very quickly about chapter 7 and chapter 12, especially because I really would like to get into the multi-dimensional linear partial differential equations, and also the distribution and transforms, which is a generalization of the Fourier of series system we have learned a lot. Okay. So don't forget that the homework. I'm sorry about that. It almost sounds like being a criminal by assigning such a tight schedule, but I do apologize for that. But there's nothing I can do. So again, please don't forget the homework is due next Wednesday. Okay, and the new homework, which is completely about chapter 6, will be assigned today. Okay, and then you're again going to have more than 1 week. Okay, which will do the week after the Wednesday after the next week. So and again, there's going to be 2 more, and then I suppose that's going to be it. Okay. So going back to chapter 6. So we have introduced the idea, okay, about the harmonic functions, about the properties of the harmonic functions, about so first of all, again, it starts from chapter 6. We were talking about 6.1, the Laplace equation and the Poisson's equation, especially like Laplace u equals to 0 is the Laplace equation, or Laplace u equals to f, which is the Poisson's equation. Okay, and again, this is in a higher dimension. Let's say ND, okay, ND space. This is the ND space. And we have successfully argued the maximum principle of the harmonic functions. Again, for any u, this kind of u, okay, this kind of u is defined as harmonic functions. Okay, and for any harmonic functions, we're having that the maximum principle. Okay, the maximum principle, which is that if u is harmonic on a connected bounded domain, D, okay, then the maximum of u and the minimum of u are both attained on the boundary, okay, on the boundary of u, and can't be attained any place, anywhere, right? Anywhere, interior of D, unless my u is a constant. Unless the ux, okay, is a constant. Again, the maximum principle tells you actually contains two parts. First of all, the maximum and minimum, they can only be attained on the boundary. Okay, first thing. Second thing, if it evers, okay, if the maximum or minimum is ever attained, okay, in the interior of the of the domain, then there's only one possibility, which is that the whole function is a constant. The whole harmonic function is a constant function, which is the most trivial one, most trivial choice. Okay, and it also it involves the following circumstance, which is that, okay, so I'm having a domain, okay, and I tell you that the maximum is attained over here, okay, both here and here, which means that there is one boundary point and there's one interior point. Most of them attains maximum, okay, then the maximum principle still applies, which means that, again, this applies to what? This satisfies that the maximum is attained in the interior, which means that if this ever happens, then again the whole function can only be a constant function. Okay, so that's actually a very, very strong argument. This is actually a very, very strong argument. Okay. And we have discussed, and we have also discussed the invariance. Okay, the invariance of Laplace Laplace symbol, okay, in 2D. Okay, we have argued that under the rigid, which means that under the rigid, under the rigid motions, okay, under the rigid motions, the Laplace, which equals to partial xx plus partial yy, okay, this symbol will not be changed. Okay, this symbol will not be changed. Which means that if I find a way of rigid motion to introduce a new coordinate, okay, which means that using the spatial translation and the rotation, okay, then under the new coordinates x prime and y prime, okay, which is again coming from x and y through spatial translation, okay, ST, spatial translation and rotation. Okay, then it also equals to partial x prime, and partial y prime. Okay, or more specifically, that means that my x prime, y prime, okay, this guy equals to let's say something like let me say okay, so b x y and then plus certain let's say certain eta. Okay, certain eta. My B is a rotation matrix. Okay, my B is a rotation matrix. My B is a rotation matrix. Okay. So this actually includes all the possible rigid motions, okay, of the coordinates. If that happens, then the Laplace symbol stays invariant. Okay, this is the first thing. And then the second thing is that, okay, so if I am if we rewrite Laplace in spherical coordinates, polar coordinate, let's say. Okay, Laplace in polar coordinate, then my Laplace actually polar coordinates, let's say r theta. Okay, then my Laplace actually equals to partial r, and then plus 1 over r partial r, and then plus 1 over r squared partial theta. Okay, I guess I don't have to state what does it mean by a polar coordinate, but that leave us one outcome, which is that, okay, if we are considering a, let's say, considering a harmonic function, okay, function that is rotationally invariant. Which means that this harmonic function is exactly the same, no matter how I rotate it, okay, around the original point, okay. So for such a harmonic function, then of course this harmonic function will not contain the variable zeta, because again, whichever angle that I come in to observe, this this harmonic function should be staying the same. It should be staying the same, which means that in this case, this type of harmonic function which is rotationally invariant should satisfy that. Okay, partial satisfy that URR plus 1 over R UR, which equals to 0. Okay, and this will leads to that my UR equals to C1 log R and then plus C2. Okay, C1 log R plus C2. And we have explained the pseudo contradiction. Okay, we have explained the paradox over here. Why? Okay, the harmonic function that is rotationally invariant could ever contain log R, which is clearly singular at the original point. Okay, we have actually explained that. That is to say, if we are talking about a harmonic function, okay. If we're talking about a harmonic function that is harmonic, okay, if that's harmonic everywhere in the circle, okay, if that's anywhere, harmonic function that's anywhere harmonic within the circle, and since it is rotationally invariant, which means that it's staying as a constant, okay, it's actually a constant on the boundary, which means that on the boundary, this is my D, okay, on the boundary, my U, actually, my Ux actually equals to UR. Okay, for my X on the boundary, okay? And then in this case, according to the maximum principle, actually I should only have what? According to the maximum principle, since the harmonic function is all the same on the boundary, then its maximum and its minimum should be both exactly the same, okay? Because they are both contained on the boundary, which means that this harmonic function is actually completely the same, just as a constant, okay, within the unit disk, okay. And if we could ever allow, okay, if we could ever allow that this harmonic function, okay, is harmonic almost everywhere, but except for the original point, then we'll be able to accept the log R. Okay. Again, what does this log R stands for? The product, okay, the UR, which equals to C1 log R plus C2, okay, this, first of all, it's a harmonic function, but defined on which place? It's defined on the whole plane, but excluding what? Excluding the original point. Okay, excluding the original point. And this actually serves as a very important, as the very important source function, okay, later when we will be talking about the solutions, okay, to Poisson's equation. Okay, so that's a very brief summary, okay, of the last class. And this class will be first talking about the invariance in the 3 dimension, and then we'll be covering 6.2, which is the how to solve the Laplace equation on rectangles and cubes. Okay, and then we'll be getting into how to solve the Laplace equation on circles or spheres or cylinders, which is the Poisson's formula. And our goal for chapter 6 is to cover in chapter 6.1 to 6.3. We'll be excluding 6.4. This is not necessary for us for now. Okay, so again, now invariance in 3D. Okay, invariance in 3D. In 3D. Okay, again, the argument is exactly the same as above. If under the rigid motion, okay, the Laplace simple, the Laplace operation will exactly stay the same in formula, which means that again, if I am having, let's say x prime, y prime, z prime, okay, if this guy equals to things like b, multiplied by x, y, z, and then plus eta. Okay? If I'm talking about this, okay? Again, my B is a rotational matrix. Okay? My B is a rotational matrix. Okay? My B is a rotational matrix, and which means that again my B should be a what? Okay, my B should be a normal matrix satisfying that B and multiplied by B transpose y equals to identity. Okay, this is the property that a rotational matrix in 3D should satisfy. Actually, you are going to find that this is the property for any rotational matrix in n dimension should satisfy. Okay, in n dimension should satisfy. Well, why is that? Okay. Why is that? This is something like if you okay. So how should I put it? How should I put it? Well, actually, you know what? I cannot find a very I cannot think of a very direct geometrical argument to tell you that why the rotational matrix in ND should be going like that. But don't worry, it actually should be very straightforward. Okay, yeah, I'm going to send something to Bryce after the class. Sorry about that. But anyway, so okay, so now if we choose to ignore, if we choose to ignore this, because again the spatial translation actually is not a problem, right? The spatial translation is not a big problem for us. So we'll be focusing on if my x, y, z, x prime, y prime, z prime is simply a rotational the rotation, the new coordinates come from the rotation old coordinate. Okay. If we're having something like that, then again, what is my Laplace u? Okay, sorry. Then what is my Laplace u? Okay. Then don't forget that my Laplace u should be uxx plus uyy plus uzz. Right? This is 3D. This is 3D. And my goal is to prove that this guy also equals to this guy also equals to ux prime x prime plus uy prime y prime plus uz prime z prime. This is my goal. I don't know it yet. However, what we are having over here is that we'll be able to write because actually let me put it this way. I will be able to rewrite ux into the x derivative of ux, and if I know what can I do to write partial x into the sum of partial x prime plus partial y prime plus partial z prime. If I know the a, b, c, if I know the coefficients over here, then I can just simply continue to do everything in the chain rule. I will be able to do everything in the chain rule. So this actually is going to be So this is actually going to be. Let me put it this way. So what we can do over here, is that this actually what you can actually find that my uxx plus uyy plus uzz this can be viewed as that I am having a u, and then so what should I so let me see if there is any way for me to express that in the linear algebra fashion. So that is actually something like, so let me put it this way. So I am not going to write down the chain rule in sums. I'm going to write everything in the matrix formula. So first of all, this of course is partial xx plus partial yy plus partial zz u. This is right, okay? And where does the partial xx, partial yy, partial zz comes from? They are actually, okay, they are essentially this, okay? They are essentially partial x, partial y, partial z, okay? And then multiply by 1, 1, 1, 0, 0, 0, which is identity, okay? And then multiply by partial x, partial y, partial z, u. Is this okay? Is this okay for everyone? This is okay for everyone? Good? Okay. And because this is a vital step. Okay, this is a vital step for us. But what we have just known about identity, we have just known that my identity actually equals to this. Right? My identity actually equals to this. And well, and it can also be written into P transpose multiplied by P. So is it good? Okay, this is the property of the normal matrix. Okay. So I will be able to write everything into partial x, partial y, partial z. This is the row vector. Okay, and then multiply. This is identity again. Then my identity can be rewritten into B transpose multiplied by B, and then partial x, partial y, partial z, u. So far so good? This is okay? So far so good? And one more step. Okay, one more step. So this can again be written into what? Again be written into the B partial x, partial y, partial z. Okay, and then this is going to actually be partial x, partial y, partial z, transpose u. This step is okay? This step is okay? But what do we exactly know about the partial x, partial y, and partial z between x prime and y prime and z prime? Okay, we actually know that B is actually exactly the matrix projecting x, y, z to x prime, y prime, z prime. So we will finally obtain something like, okay, this is actually partial x prime, partial y prime, partial z prime, okay? And then multiply by transpose, multiply by partial x prime, partial y prime, partial z prime, u. So far so good? Okay? And then finally, this is actually partial x prime, partial y prime, partial z prime, and then multiply by product vector, partial x prime, partial y prime, partial z prime, u. Okay? And then finally, we obtain, this is actually partial x prime plus partial y prime plus partial z prime, u. Okay, I have just trying to rewritten. This is again a way to exploit the linear algebra. Okay, in our computation. Okay, in our computation of of operators. Okay, if you feel that you are uncomfortable with this, or you feel that you cannot recognize what exactly we did, okay, over here, then probably it's a good time for you to turn back to page 27 of the book, which again, the type of second order equations, we have done a lot of these kind of things. Okay, we have done a lot of these kind of things, of the linear transform, okay, especially for the second order operators. The second order, the linear transform, second order operators. Okay, we have learned that in 1.6, okay, and this is the time that when our previous efforts paid off. So that's great. Okay, so again, it confirms that okay, the Laplace operator, okay, will still stay the same. Okay, it will still stay the same. Okay, under the three-dimensional rigid motions. Okay, and another related topic, okay, for 3 dimension is that, okay, how to rewrite, okay, another question is that how to express, okay, Laplace u, okay, in polar coordinates. Okay. How to express Laplace u in the polar coordinates? Well, what I'm going to see is that the polar coordinates actually is something as follows. Okay, the polar coordinates is something like r theta. Okay, phi. Okay, this is the symbol used by the book. R theta phi. Okay, again, the polar coordinates in 3D. Okay, the polar coordinates in 3D is this. This is our usual x-axis, y-axis, and z-axis. Okay? And the polar coordinates is this. So I'm having a point in the 3D space. Of course, the first variable r describes how far is it away from the origin. Okay, this is exactly the same as the 2D polar coordinates. Okay, and the second angle theta. Okay, the second angle theta. It tells you the angle that it is away from the z-axis. Okay, the angle that is away from the z-axis. But again, there's still a cube. Okay, there's still there's still a cone. There's still a cylinder cone. Okay, that on which all the vectors satisfy that it is away r from 0, okay, and it's theta angle away from the z-axis. Therefore, we will be needing one more, okay, angle, okay, which is first of all this is my x, okay, and this is its projection. This is the projection of the vector on the xy plane. Okay, and then we'll be concerning what is its angle away from the x-axis. Okay, what is its angle away from the x-axis? So we'll be needing one distance and two angles. Okay, and two angles to determine what is the polar coordinate. Okay, what is the polar coordinate for a vector, okay, in the 3D space, in the three-dimensional space. This is actually also related to how do we localize ourselves, okay? How do we find our location on the Earth, right? We need a 2D coordinate, but you see these 2D coordinates are always in what? Actually always in degree. Okay. This is again assuming that the Earth is a perfect sphere, though it is not, but assuming that it's a perfect sphere, okay, and then we'll be needing two angles, okay, to determine the exact location of ourselves. But now it's just that, assuming that we will be able not just translate from one place to another on the sphere, okay, but we'll be able to go down and go up, okay, into the ground, outside of the ground. Then actually we will be needing the r. Okay? We will be needing the location, the distance r, okay, for us to provide the 3D coordinates. Okay, and I can tell you that after some computation, okay, and I don't intend to show that. If you are interested in the computation, you should definitely look into page 159. Okay, page 159. But let's directly go to the results, which is that the Laplace u, okay, in the 3D, which equals to uxx plus uyy plus uzz, okay, this guy actually equals to, okay, so urr, written, if I write everything into the polar coordinates, actually equals to urr and then plus 2 over r, okay, ur, and then plus 1 over r squared sine theta, and then let's say it's actually, okay, sine theta, u theta, and then plus 1 over r squared sine squared theta, and then u phi phi. Okay, u phi phi. Complicated, right? But again, I promise you that I won't be asking you to compute, to perform the computation. It's not part of the class, and I don't think it is that important as long as you already know as long as you know how to do it. Okay. Question?
I think theta and phi should be exchanged with each other in the drawing. I'm not sure. I remember there's a convention for spherical coordinate. I'm not
to
sure.
To be honest, okay, in this paragraph, I'm just simply copying everything from the book.
Okay.
Okay, I'm not really familiar with the 3D polar coordinate myself, because I don't use it in my research. Okay, so I'm just simply copying everything in the book. If there's any mistake, okay, it's the book's problem. Okay, but again, this in principle is not hard to verify, not very hard to verify. Okay, with vector calculus, it's just about some amount of time. And if you would like to hone your skills and have a better understanding of the 3D polar coordinate, actually I encourage you to try to repeat the processes of the book on page 159. But here I will say over time. I'm not getting into that. Okay, and again, the question is about how to obtain a 3D harmonic function. Okay, that is rotational, invariant. Okay, how to obtain a 3D harmonic function that is rotational invariant. And again, that means that for my harmonic function, 3D harmonic function, r theta phi, okay, that is rotational invariant, that means that it has nothing to do with the angle, with the choice of the angle. It has only one thing to do with the distance, okay, which means that it will be able to be rewritten into UR. Okay, we are able to rewrite it into UR, and therefore any partial derivative on the directions of theta and on the directions of phi, okay, will be eliminated. Okay, which means that now instead we're actually dealing with a very straightforward partial differential equation, which is now is URR plus 2 over R UR equals to 0. Okay, and here is what I would like you folks to do some computation. Okay, do you mind again try to derive what 3D harmonic function that is rotational invariant looks like? Okay. Yeah, please pull out your pen and your scratch paper or your tablet. Try to do some computation. This is again equivalent to a first order ordinary differential equation, right? this actually doesn't have to take a long time, right? Okay. So again, let's say my VR is actually UR, okay, the first order derivative of U on R, okay, and then that means that actually my dV dr, okay, and then plus 2 over RV equals to 0, right? Okay, and then it's not hard to see what is my V. What is my V? Can you just say it out? What is my VR? Okay, my VR is actually, okay, so negative, okay, negative. So, let me see. So sorry, this is a little bit confusing because the V and R are actually alike. Okay. The R, okay, and 2 over R and V. Okay, what is VR? What is VR?
Constant times the
It's actually something like, okay, let's say C1R the negative 2 times.
Oh, right.
to me,
C1R negative 2 times.
to me.
Okay. And therefore, my UR, okay, my UR is negative, let's say, that's C1R the negative 1 times and then plus C2. Well, of course, there's going to be a 1 or 2 or something. But again, it can be absorbed by my C1 and C2. So it doesn't matter. So is it good? Okay, this is my UR. But again, what kind of function is this? What kind of function is this? Or let me try to write it down again into Cartesian coordinates. Okay, so UR actually that equals to R is what? R is actually the square root of x squared plus y squared plus z squared, because that is the distance between this point and the original, right? Okay, so there's actually negative C1 and over the square root, okay, of x squared plus y squared plus z squared, and then plus C2. This is my UR, or UXYZ, U X Y Z. Again, what kind of function is this? Is that continuous everywhere? Is this function continuous everywhere? Okay, then if this is not continuous everywhere, where is the discontinuous one?
The origin.
Origin, right? When we are getting into the origin, the R is approaching 0, therefore 1 over R is approaching infinity. Okay, which means that again, this so-called harmonic function, okay, it has a singular point. But why is that? Again, can you please explain why is that? Using the analogy of what we have done in the 2D case. If again I'm asking for a 3D, if I'm asking for a 3D harmonic function that is rotationally invariant, what does that mean? That means that
It's constant.
previously on a square, but now on a sphere.
Sphere is a constant.
Okay, on a sphere, this function is what?
Constant.
Constant. This function is constant because it's rotationally invariant, right? But if it is harmonic everywhere inside within this ball, okay? If it's harmonic everywhere within this ball, and it is constant on the boundary, what can we conclude? Then the maximum and minimum are both attained on the boundary, which is the sphere, which is a constant. Which means that again, this function can only be what? This function can only be a constant function, okay, within this, okay, within this ball, okay. And now, why we could ever obtain a function that is singular at the original point? This is actually when we are solving the first order ODE, okay. When we are solving the first order, or actually the second order ODE, we did not pose the boundary condition. Okay, we did not pose the boundary condition that when R equals to 0, my u has to be finite, right? If I pose the initial condition that when my r is 0 and u should be finite, then actually I won't be able to have this function in my solution. I will only be able to obtain a what? A constant function, right? But by allowing that the original point could be a infinity, by allowing that the original could be infinity, I am allowing that, okay, here, the original to be singular. Okay, again, this is a harmonic function. This is a harmonic function in 3D. Okay, this is harmonic. This is a harmonic function in 3D and rotational invariant. And, okay, but not at the original point. Not harmonic. Okay, at origin, the origin. Okay, or singular at origin. Depends on how you see it. Okay, so that's good. So this is the idea of the harmonic functions. Okay, and it's rotational invariance in 2D and 3D. Okay, so now with that basic information in our on hand, okay, we will now be able to start for actually solving some more complicated part of the Laplace equations and Poisson's equation in 2D and 3D. Okay, so 6.2, we'll be talking about Laplace equations on rectangles and cubes. Okay, on rectangles and cubes. So what does it mean? So let me take the example. Okay, let me take the example of the book. So now let's say I know that I know that the Laplace u, okay, equals to 0. This is the Laplace equation, okay, in a rectangle, D. And, okay, this is my rectangle, okay, this is my rectangle, in rectangle D. But it's just that, the boundary conditions are a little bit cumbersome. Okay, the boundary conditions are a little bit cumbersome. And more specifically, let me exactly quote what is set up on the book. So on the left boundary is to satisfy that u equals to jy. Okay, of course this is the x-axis, this is the y-axis. Okay, this is the x-axis, this is the y-axis. Okay, and on the right boundary, okay, on the right boundary, this is ux equals to ky. Okay, so not the same, right? On one side is u itself, which is Dirichlet, not homogeneous at all. On the right side is Newman, again not homogeneous at all. And on the lower side is actually uy plus u, okay, equals to hx, which is a Robin boundary condition. Okay, and on the top is actually u equals to gx, which is again a inhomogeneous Dirichlet boundary condition. Okay, so you can play this game as much whatever you want. Okay, you can set an arbitrary boundary condition, which is on the left, on the right, on the bottom. Okay, and 6.2 discuss how do we solve this type of boundary value problems for the Laplace equation. Okay, for Laplace equation with the help of Fourier series. Okay, and before we even start to dig into the details over here, let's first talk about the general idea. Let's first talk about the general idea of solving this type of equation, this type of problems. First of all, you see, the four different sides are what? On the four different sides, we're having exactly the inhomogeneous boundary conditions. And we are always actually not so happy with the inhomogeneous boundary condition because it is always needs some special handlings. Okay, But instead, what type of boundary conditions that we like? We always like what? We always like the homogeneous boundary condition, right? We always like the homogeneous boundary condition. So the first idea, okay, so for the first step one, the first step of dealing with such a Laplace equation with 4 sides of non-inhomogeneous boundary conditions. Yes?
Why we specifically assign these 4 boundary conditions at these 4 positions?
What do you mean?
I mean, why at the bottom we just assign the roaming condition? Can we change it to?
You can assign anything that you want.
Oh. Okay.
Yeah, it can be Dirichlet.
So this is just for an example.
Yeah, just for an example.
Oh.
Just for again, this is for an example. Of course, you can switch. You can switch the left and right, or left and bottom, or top and bottom, or robbing on the 4 sides, or Dirichlet on the 4 sides. It's all your choice. All your choice. Okay, I'm just trying to demonstrate an example. Okay, I'm just trying to demonstrate an example. Let me try to say it out. Okay, these things are arbitrarily chosen. Okay, these things are arbitrarily chosen. But actually, the sneaky part is that actually they are chosen to ensure that their homogeneous version, okay, are symmetric. Okay? Because if they are not symmetric, then actually we won't be able to use the Fourier transform, the Fourier series, right? But we're not there yet. We're not there yet. So let's talk about our step 1. Okay, let's talk about step 1. The step 1 is that, okay, first decompose. Okay, decompose the solution U, okay, into 4 parts. So U equals to U1 plus U2 plus U3 plus U4. What does it mean? That means that I am having 4 sides of inhomogeneous boundary conditions. That's too hard for me. And I don't want to deal with that in one step. Instead, okay, I would like to decompose the U into 4 parts such that each part will only have 1 side of inhomogeneous boundary condition and 3 sides of homogeneous boundary condition. Therefore, okay, I will be able to solve the U1, U2, U3, and U4 respectively, and then finally, again, compose them to obtain my full solution U. So more specifically, what is my U1? Okay, my U1 is the solution. Okay, my U1 is the solution to the following problem. Again, my Laplace U equals to 0, okay, in rectangle. The same rectangle, D, okay, everything is the same except that, U1, okay, except that now I am having my U1 equals to GX, okay, which means that the U1 has exactly the same inhomogeneous boundary condition as U, but on the other 3 sides, my U1 is actually enjoys the homogeneous boundary condition. So actually my U1 equals to 0. Here, my U1x, okay, equals to 0. And U1y plus U equals to 0. I'm trying to solve. So again, let me explain my logic again, right? So first of all, so based on the old question, I'm defining a new question. The new question, the relation between the new question and the old question is that, okay, first of all, it has exactly the same boundary condition on only one side, which means that originally it was inhomogeneous, now it's still inhomogeneous. So that's good.
I think it's
okay. And now, originally, for all the other 3 boundary conditions in the original question, they are now changed, okay, directly changed to the corresponding homogeneous boundary conditions. And we need to be very careful over here with that. When you are doing the changing, okay, we should ensure that the boundary condition type is still the same. Which means that originally you used the jy, what kind of boundary condition is that? It's Dirichlet. It's an inhomogeneous but Dirichlet boundary condition. Therefore, in the homogeneous type of question, it should be a homogeneous but still Dirichlet boundary condition. On the right side, it's what? It has been inhomogeneous Dirichlet. Oh, sorry, inhomogeneous Newman boundary condition. So after the change, it should be again changed to a homogeneous Newman boundary condition. Okay? So this is my U1. My U1 should satisfy this. And let me just not be lazy and just write down, let's say U2. Okay? My U2, again, it is satisfying the same thing. But now, okay, let's say now my U2 satisfy that U2 y plus u equals to hx, which is exactly the same as before. Okay? So now what can you say about the other three boundary conditions for U2? What can you say about the other three boundary conditions for U2? So my U2 on the left hand side, my U2 should be what?
0.
Jy?
0.
0. On the right side, my U2 should satisfy what? U2 be 0?
Yeah.
U2x be 0, right? Because again, the right hand side is what? Right hand side satisfy. Originally, the right hand side satisfied a Newman boundary condition. So again, the new question is still satisfy a Newman boundary condition. What about the top? My U2 should satisfy what?
0.
0. Okay, my U2 should satisfy 0. So this is going to be U2. So good? Okay. And what about my U3? What about my U3? My Laplace U3 equals to 0. Let's say now, this time, the U3 turns to the left, okay, which means that my U3 equals to jy. Okay, my U3 equals to jy, which is exactly the same as before, as the origin. What about the other three sides of U3?
0.
Here it should be U3 equals to 0. Here it should be what? U3 what? U3x equals to 0. And here it should be what? U3 y and then plus U3, which equals to what? 0. Yes. Question?
I think for the former two, it should be u1 y plus u1 equals 0 and u2 y plus u2 equals
Sorry, can you say it louder?
For the former two solutions of u1 and u2 on the lower part of the rectangle, it should be u1 y plus u1 equals to 0 and u2 y.
Oh yeah, you're right. Yes, you're right. Yes, thanks for catching the bug. Okay? Okay, now you tell me what is U4? What is U4? U4 satisfied, U4 is also harmonic, but what is the boundary condition for U4? What is the boundary condition for U4?
The right.
Okay, on the right hand side, U4 should satisfy what? X equals to K1. Okay, and then the other three?
0.
Okay, here it should be U4 equals to 0. Here it should be what?
0.
U4, okay, on the top it should be U4 equals to 0. And on the lower part, should be what? U4 y. And then plus U4 equals to 0. So what's good? Okay, so you see, now this is what we mean by the decomposition. Okay, we're decomposing the solution U into 4 parts. Each part satisfies only one side of the inhomogeneous boundary condition, but 3 other sides of homogeneous version of the boundary condition. Now, you see, so we haven't said that this will definitely work, but assuming that I can already solve my U1, U2, U3, and U4, after I add them up, okay, what can I say about the boundary condition of their sum? What can I say about the boundary condition of their sum? For example, because you see, after I have solved U1, U2, and U3, U4, the behavior on the boundary should be exactly what? The behavior of the sum of the boundary should exactly be directly summing up the four boundary conditions, right? So let's check the left hand side, right? U1 is to 0, U2 is to 0, U4 is to 0, but U3 is to JY. So what can I say about their sum? What can I say about their sum? What I'm talking about the sum of U1, U2, U3, and U4 on the left hand side. What can I say? JY. What about the right hand side? What about the right hand side? U1 x equals to 0, U2 x equals to 0, U3 x equals to 0, but U4 x equals to ky. So what about their sum? Okay, what about their sum? Why is ky? Why is ky? If so let me put it this way. If I have ever changed this Newman boundary condition, Newman homogeneous boundary condition, to be a Dirichlet homogeneous boundary condition, will that still hold? Will that still hold? Will that still be okay? If I, for example, if I'm changing the U1 x equals to 0 to U1 equals to 0, can I still say that their sum satisfy the Newman boundary condition that Ux equals to ky? Can I say that? No, not anymore. Right? That's exactly the reason that we are requesting every homogeneous boundary condition, okay, of these sub-problems to stay exactly the same as the original problem, as the original type of the boundary conditions. Okay. So does the upper bound and the lower bound. Well, the lower boundary you can see it most clearly, right? This is all because what? This is all because the differentiations are linear. Okay, the differentiations are linear. So again, let's say when you are summing up the let's say the bottom boundary condition, right? This guy, which means that when you are doing something like, okay, so now let's say U equals to U1 plus U2 plus U3 plus U4, then on the bottom boundary, okay, on the bottom boundary, okay, what can I say about Uy plus U? What can I say about Uy plus U? This is actually U1 plus U2 plus U3 plus U4 Y, and then plus U, right? And and then plus U1 plus U2 plus U3 plus U4, and it is exactly because the differentiation, this step is linear. Okay, the differentiation is exactly linear. So we were able to obtain this guy as Uy, U1y, and then plus U2y, and then plus U3y, and then plus U4y, and then plus U1 plus U2 plus U3 plus U4. And what do we know? We know that this guy is 0, this guy is 0, this guy is 0, but this guy is actually hx. So finally, it is hx, which exactly satisfies the original boundary condition. So that's good. So this is the first step of carrying everything apart. Okay. Then the next step. Okay. Next step. So this is my step 1. Okay. Well, by encountering this strategy at the first time, it's a little bit hard to digest. But after we are familiar with that, it's actually very problematic. Okay. So whatever boundary condition that you have, just put it. Okay. Just first of all tear them apart, and then try to split the original question into several sub questions. Okay. And then try to solve every sub questions one at a time. So now step number 2, okay, is to solve each sub questions. And we'll be solving question number 1. Okay, we'll be solving question number 1, which is okay. So the example is solving question number 1, which is that U1 log plus U1 equals to 0. Okay, and we are having the 4 boundary conditions as U1 equals to gx, and then on the bottom U1y plus U1 equals to 0. And here is actually U1 equals to 0. Here is U1 x, okay, equals to 0. Okay, we'll be solving this. Okay, we'll be solving this. why don't we take a break for 5 minutes, okay, and then we come back to the specific solutions of this sub question.